Once the applied stress exceeds the yield stress, the deformation becomes permanent. The planes of atoms have slipped. Now there is a permanent shape change. The slip in the planes of atoms is permanently, so they can no longer spring back to their original shape. We've reshaped the metals. The metal has now been permanently stretched. It is permanently no longer. Now it is elongated. So we've stretched the metal. It is now permanently longer. Because the metal has been permanently elongated, when we release the load, reduce the stress back to zero, the metal will no longer elastically spring back to its original starting point. We now experience and measure permanent deformation or elongation. If you look at the graph, as we've released it, the straight line has dropped back to zero stress, but there is now permanent elongation. We've got a permanent change shape. The planes of atoms have moved. Once the applied stress exceeds the yield stress, the deformation becomes permanent. The planes of atoms have slipped. The deformation is permanent, and we term this permanent deformation plastic. So above the yield stress, the metal behaves plastically. We reshape and deform it permanently. Up to the yield stress strain relation, the relationship is a straight line linear. And we say up to the yield stress, the metals behave elastically. Above the yield stress, the deformation is permanent, and we term this deformation plastic behavior. And it is plastic behavior because we reshape the metal, we slip the planes of atoms. So once a metal has yielded, on release of the stress, it is permanently plastically deformed. The slip in the planes of atoms is permanent. If we look at grains, we change the shape of the grains. So once a metal has yielded, on release of stress, the grains are permanently plastically deformed. We change the shape of the grains. The greater the applied stress, the greater the deformation of the grains. So you can see we've reduced the load, it's come back to zero, and we've now changed the shape of the grains. In this one, we've elongated them. Once a metal has yielded, the grains have been permanently deformed, so the metal has been work or strain hardened. This deformation has occurred at ambient temperature, so we have cold worked the metal. The work or strain hardening has increased the strength of the metal. Once the metal has yielded, the plastic deformation is cold working as the planes of atoms slip and lock up. As the stress is increased, the degree of slip increases the deformation of the grains. As the severity of the deformation increases, because of the lockup effect, the deformed grains are more resistant to further deformation, that is, work or strain hardening. Thus, the stress required to induce more slip, more grain deformation, increases with increasing deformation. In consequence of the strain hardening, the deformation of the grains, any further deformation requires a further increase in strength. Hence, work hardening or strain hardening. So as we change the shape of the grains plastically through work hardening, every change requires a further increase in stress, increasing the strength of the metals with each subsequent deformation. We need to go back to the yield point, and textbooks refer to the yield point of metals by many terms, all have the same meaning. Yield stress, yield point, elastic limit. Remember, up to the elastic limit, metals behave elastically. Above the yield or the elastic limit, they behave plastically. Now, aluminium has a poorly defined yield point, yield stress. So for engineering purposes, the yield point, the yield stress, is taken as the stress required to produce a 0.2% permanent deformation. That means when we can measure a permanent increase in gauge length of 0.2%, the aluminium is taken to have yielded. Now, products are designed to be subjected to stresses in service below the yield strength with a safety margin. A safe margin below the yield stress, so within the elastic stress. So designers design components to work in the elastic area well below the yield point. Once you've gone over the yield point, they would deform, bend, and fail. Now, as the stress increases above the yield stress, so does the deformation of the grains and the degree of work of strain hardening. Each deformation increases resistance to further deformation, so we see an increase in the stress load, the force required. As the stress increases, so does the deformation of the grains and the degree of work or strain hardening. The slip of the planes of atoms increases the strength. Now, as we carry on increasing the stress, so as the stress is increased, the slip in the planes of atoms is so great that the metallic bond eventually fails and the atoms start to pull apart. As the atoms pull apart, the cross-sectional area is reduced, so the metal can no longer support the applied stress. The stress plateaus or levels out. So we can see here that the atoms have pulled apart and the stress strain line has almost gone horizontal. The plastic deformation at this point is maximum. So the stress plateau is maximum, and this is the maximum stress, load, or force that the metal can support. This is the maximum stress. We term this the maximum breaking stress or the maximum tensile stress. And different textbooks use different terms for this plateau. Ultimate tensile strength, maximum breaking load, maximum breaking stress. This is the maximum stress load that the metal can support. If we carry on loading beyond the maximum breaking stress, the metallic bond completely fails and the atoms part and the grains pull apart. The parting grains, atoms, can no longer support the applied stress, so the measured stress falls off. The parting atoms reduce the cross-sectional area, resulting in localized necking. The localized increase in the parting of the grains and the associated reduction results in a reduction of the measured stress, and eventually you get total parting, and at this point the atoms have failed. So once we're over the maximum breaking load, the atoms are being pulled apart, the metallic bond is failing, the load is dropping off, and eventually we pull the atoms apart. After failure, the neck down plastic deformation is termed ultimate elongation. So remember, above the yield stress, up to the maximum breaking stress, and beyond the maximum breaking stress, we are plastically stretching, pulling the atoms apart. So after failure, we've got a lot of plastic deformation, and we term that plastic deformation ultimate elongation. And if we piece the test piece back together, we can measure that elongation as a percentage elongation over the original gauge length elongation. I trust you've enjoyed this module. Please see some further reading. Thank you very much.